dx, then that's going to be something like this. And that's like taking, well, you're going to be taking a small step in the y direction as you move in the x direction. And we want to know what the ratio dy over dx is. And we said that if this graph is f of x, then this is going to be equal to f prime of x, the derivative of f at x. And this is also the slope of a line. So we'll get to that actually in a second, but we know that this is also the slope of a line tangent at this point. That line would have the slope m is equal to f prime x. So now in 2 dimensions, we want something fairly similar. So here are our 3 coordinates, x, y, and z. And now we're going to have a surface over here. And we would like to know what happens if you take a small step in the x direction while keeping the y variable constant. So here's our dx, and that would be something like that on our surface. That would end up being something like this on the surface, which in the z direction would end up being, let's say, something like that. And this would be our dz. And we would like to know what this is. What is dz over dx? But in this situation, we're keeping the y constant. So we actually rewrite this into the partial of z with respect to x. We just use a different notation. Instead of d, we're now using partial derivatives. But it's doing the same thing. We are saying, okay, I want to take a small step in the x direction. How does that change my z direction, assuming that y is left constant? And another notation that we use for this is f of x. The partial of f with respect to x. Then in the y direction, so you can think about taking a small step in the y direction, keeping x constant. So this over here would be dy, or now it would be I'll just use dy like that. And so again, you would want to know a small step in the y direction, how does that change my z direction? So that would be partial y with partial z with respect to y, which would be equal, just to clarify some stuff, this is the surface z is equal to f of xy. Okay, so then this thing is equal to f of y. Any questions about this? Okay, so when we want to define a derivative, we're going to use limits. So the same way in Calc 1, we said that the definition for the derivative, f prime of x, was equal to the limit as h goes to 0 of f of x plus h minus f of x over h. So similarly, in 2 dimensions or 3 dimensions, when we look at f prime at x comma y, well, this is not really defined well because that prime does not really tell us if we are differentiating in terms of x or y, but partial of f with respect to x will be the limit as h goes to 0 of f of x plus h comma y. But you see, y over here doesn't get an h because we're just keeping it constant, minus f of x comma y over h. And similarly, f with respect to y of xy is going to be equal to the limit as h goes to 0 of f of x comma y plus h minus f of x comma y over h. Any questions about this? Okay. So, no, sorry, here. Okay, so like we said, partial of f with respect to x is just can be written like that. Partial of f with respect to y can be written like that. This would be if we want to plug points in. So let's do an example. So they ask us to compute the partial derivative of fxy is equal to x squared y to the fifth. So f of xy is equal to x squared y to the fifth. And they want the partial with respect to x and y, okay? So partial with respect to x of x comma y, well, that's just keeping y constant, so that would be 2x y to the fifth power. Okay, partial with respect to y, xy, would be x squared times 5y to the fourth power. Again, now we're keeping x constant. Okay, any questions about this? Okay. This. Okay. So the next thing that they show us is some pictures about how we can interpret this in terms of slopes of lines. So let's go back here. If we have a surface, so here's my x, here's my y, and here's my z, here's the surface. Another interpretation, let's say, of the partial of f with respect to x at a point AB. So we can look at a point AB, and if we want to take the partial with respect to x, we can imagine a plane that, well, it definitely cuts through the surface, and it would look something like this. Second. Okay. And the point AB on the surface would, let's say, be this point over here. And so then the derivative would give us the slope of the line that's tangent at this point. So for this line, m is equal to f of x AB. Okay, similarly, in terms of the y direction, we can again look at our surface. And again, we're at the point AB, which on our surface would be this point. And this time, we are going to take a plane that slices in that direction. And now when we take the partial of f with respect to y at AB, that's going to be equal to the slope of this line over here, tangent to that curve. Any questions about this? Okay. So they want us to calculate these things where g of xy is equal to, okay, so g of xy is equal to y squared over 1 plus x squared cubed. And they want us to find gx of 1, 3 and gy of 1, 3, right? Yeah, so first we need to figure out what what gx of xy is. So that would be the quotient rule over here. We're treating y as constant and only differentiating with respect to x. So that would be this times the derivative, 1 plus x squared times the derivative of y squared, which is 0. And then negative y squared times the derivative of this thing, which is going to be 3 times 1 plus x squared, all of this times 2x, over 1 plus x squared to the 6th power. So just doing the quotient rule. And then x13, now this is going to be negative 9 times 3 times 4 times 2 all over 2 to the 6th power. Okay, now the partial of g with respect to y at x, y is going to be, so now we just take this derivative with respect to y, which is easy. The bottom part is just a constant, so it's going to be 2y over 1 plus x squared cubed. And so then gy13 is going to be equal to 6 over 2 cubed. Any questions about this? Okay. So when we compute these derivatives, we can once again use the product rule, the chain rule. It's exactly like the one-dimensional derivative with treating one of the variables as constant. So they ask us to compute the partial of this thing with respect to y, ln of xy minus 2y squared. So ln of xy minus 2y squared. And they want the partial of this with respect to y. Good. So this is going to be 1 over this thing, xy minus 2y squared. And then you have to do the quotient of this thing inside, again, imagining that x is a constant. So that would be x minus 4y. And this would be the answer. So that would be x minus 4y over xy minus 2y squared. Any questions about this? Okay, I'm going to skip this example. So let's go on to the next example. And they tell us that all of this works with even more variables. So imagine instead of just an xy, we have x, y, z, w as an input, and then something else as an output, which would basically mean that our domain would be something like this. Here's x, y, z, and w in a 4th dimension. Any point here would have 4 coordinates, x, y, z, and w. And the output would be in a 5th dimension, which I'm not going to even draw. So in our case, we have f of x, y, z, w is equal to exz plus y, exz plus y over z squared plus w. Z squared plus w. Good. And they want us to find f of z 0, 0, 1, 1. They want us to find the partial of f with respect to z at 0, 0, 1, 1. Okay. So once again, this involves the quotient rule. And what this would mean over here is you're trying to take a small step in the z direction somewhere, keeping everything else constant, and seeing how the output, your f, changes. So this is going to be, by the quotient rule, we're going to have the bottom part times the derivative of the top part. So z squared plus w times exz plus y times x, because everything else is constant up there. Okay, minus the top part, exz plus y, times the derivative of the bottom part, which is 2z, over 2z squared plus w, all of this squared. Any questions about this so far? Okay. So now plugging in, okay, sorry, 1 second. This would be x, y, z, w. So now the partial of z, with respect to z, at 0, 0, 1, 1 is going to be equal to, so over here you have this x multiplying everything, so this will be 0, so it'll be negative, and over here you're going to have 1, because the x is 0 and the y is 0, it is 0, times 2z, so times 2, and the bottom we're going to have z squared, which is 1, plus w, so that's 2 squared. That would give us negative 1/2. Any questions about this? Okay. So I'm not going to do this. You don't really have to know how counter maps estimate partial derivatives. So let's continue with higher order partial derivatives. So we can take the partial of f with respect to x, and then we can differentiate that with respect to x. So then we take the partial of f with respect to x and differentiate that with respect to x. Or we can take the partial of f with respect to x and then differentiate that with respect to y. Okay, and so on and so forth. So there are 4 things that we can do: xx, yy, xy, and yx in 2 dimensions. And in terms of the partial derivatives, they would read as the partial squared of f with respect to the partial of x squared. This would be the partial squared of f, partial of y, partial of x, and so on. Any questions about this? So they want us to calculate all the second partial derivatives of this. F of xy is equal to x cubed plus y squared e to the x. So f xy is equal to x cubed plus y squared e to the x. So what are all the partial derivatives of this? So first we have to look at the partial of f with respect to x, which is equal to partial of f with respect to x, which is equal to 3x plus y e to the x. Okay, now the partial of f with respect to y, which is equal to partial of f with respect to y. Now that's going to be just e to the x. Yeah, because this is a constant, the y disappears. Good. Now the partial of f with respect to x is going to be, you differentiate this one with respect to x, we're going to get, oh, this is squared. Yeah. Okay. We're going to get 6x plus y e to the x. Okay. The partial of yy, now we're differentiating this with respect to y, that would end up being 0. Oh, 1 second. This thing is squared. Okay, so some of this is different. This thing is squared. This thing over here will be 2y e to the x. This over here is just going to be that, and then this thing is squared. Okay, and then this thing is going to be 2e to the x, okay? Then the partial of x with respect to y, now that's going to be, so now I'm taking, so this is 0, and that would be 2y e to the x, 2y e to the x, 2y e to the x. And the partial of y with respect to x, now I'm going here, oh, sorry. I'm going to here, this equation, and I'm taking the derivative with respect to x, which would just be 2y e to the x, same thing. And you can see that these are equal, and there is a theorem that says that, well, in most cases, in most nice cases where things are continuous, so we'll see some of the assumptions, but these two are equal. F of xy is equal to f of yx. Any questions about this? Is it clear?
Yes.
Thanks. Okay, so now they want us to calculate the third thing of this, x cubed plus, yeah, so same thing. So now to the xy, they just want us to add something. So xy, and then they want us to differentiate with respect to y again. Yeah. So what is f of x, y, y? So that over here would just be 2e to the x, 2e to the x. Good. Okay, so let's continue. So this is the theorem I just mentioned, that the partial of f squared and xy is equal, or the partial of xy is equal to the partial of yx. So partial of xy is equal to yx. And they ask us to verify that for w is equal to e to the u over t. So w is equal to e to the u over t, and this is equal to f of ut. Okay, so f of u is going to be equal to e to the u over t. F of t is going to be e to the u over t times -1 over t squared. Just doing the chain rule of the inside part. Oh, 1 second. That times derivative of that. Oh, maybe there's a u up there. U? Yeah, probably. T times the derivative of u is 0 minus u times derivative, yeah, okay, over t squared. Perfect. Good. Then partial of ut is going to be e to the u 1 second. Yeah, given e to the u over t times, again, -u over t squared. Yeah. And then yeah. Well, let me see something quickly. Yeah. Okay, fine. Okay, so then the partial of, so this is the partial of u with respect to t, good. And then the partial of t with respect to u, that's going to be, so that comes from here. That would be this times the derivative of this, which would be eu over t times -1 over t squared plus this -u over t squared times the derivative of this, which is eu over t. Yeah. So, maybe, yeah, I didn't do the chain rule over here. That's the problem. no, I did. This is u, this is t. ut comes from here. No, we don't need to do the chain rule. Okay. So are these two equal? Well, part of it seems equal, but then there's a part that is not. Let's see. Okay, partial t, u over t, that, okay, that is good. That's what we have. And then this with respect to u, the chain rule gets you to that. And on the product rule, okay. Okay, let's try this again. Okay, so f of ut is equal e u over t. F of u comma t is equal to e to the u over t. So partial of f with respect to u is going to be equal to e to the u over t. Okay, that's correct. And so then partial of f with respect to oh, 1 second. Yeah, you need a chain rule in here. So that would be times the derivative of this top thing, which would be 1 over t. Is that correct? Partial of, yeah, okay. I guess that was what I was missing. Okay. Good. So now the partial of this with respect, okay, so now you have u and you have t. Okay, perfect. Now this is going to be this times the derivative of that, so e u over t times -1 over t squared plus 1 over t times the derivative of this with respect to t, which is e to the u over t times -u over t squared. Okay, so then the partial of this with respect to t is going to be eut, e to the u over t times the derivative of this thing, which is going to be negative u over t squared, plus, and then you're going to have 1 second, no pluses. Yeah, so that's that. Okay, and then we have f of tu is going to be, okay, this times the derivative of this will be e u over t times -1 over t squared plus, and then you're going to have -u over t squared times the derivative, so then we'd have e over u over t times 1 over t. 1 over t, good. So how does this work out? This part is equal to that part, and this part is equal to that part. Perfect. So we have that f of ut is equal to f of tu. Any questions about this? Okay. So they say you can take many partials over here. And, okay. And they ask us to calculate the partial derivative of this thing. but I'm not going to do it. So I think we're going to stop here. In summary, the definition of the derivative is similar to the one-dimensional definition. These are the four most important derivatives in a sense, and obviously you have f of x and f of, with respect to y. And I think we're going to basically finish here. So are there any questions about any of this? No? Any questions about anything else? Okay, then have a nice weekend, and I will see you next time. Bye.